configuration and the RS convention. So we just learned about enantiomers and how they differ in this arrangement around the stereogenic center. When we talk about a configuration, we've used this word before, configuration has to do with the arrangement of the groups. So enantiomers are another type of configurational isomers. Cis-trans isomers are also configurational isomers. A pair of configurational isomers will have atoms that have the same bond pattern. The atoms are all connected in the same order, but you can only interconvert. You can only make one into the other by actually breaking at least one bond and remaking it. The other sort of isomer is a conformational isomer. These are both stereoisomers in that they differ in arrangement, but a conformational isomer has the same bond pattern, but you can interconvert it by bond rotation. And so that's where we were talking about staggered versus eclipsed things. So if we make up another molecule here, we can have these two hydrogens lined up, and that is an eclipsed conformation. We can rotate this bond and have them staggered, and that's a different conformation. We can keep rotating it, and because these groups are different, we can get different alignments. But there's really only one molecule because this bond can rotate, and so these are conformations. They're actually the same molecule. They can just spin around. In contrast, no, that's not one of them. I destroyed my chiral compound. You can't convert one chiral molecule into another just by rotation around double bonds, because it has to do with how the things are bonded to the carbon itself. So constitutional isomers, I'm just trying to review this for you because it is confusing, all these different kinds of isomers. Constitution, these differ in their constitution, in their makeup. Okay, and so this is where we have a branched alkane or a straight chain alkane. They differ in how the atoms are actually connected. So that's a different group. Back in, I think it was chapter 2, there was a nice table that showed you the different kinds of isomers. So refer to that if you need help with that. So the RS convention is a way of specifying which enantiomer we're talking about without having to draw the structure. And so what we do is we assign priorities to the 4 different groups. And we'll go over how we assign priorities in just a minute. But for this example, we're just looking at letters, and we're going to have the priority be alphabetical order. So A, B, C, and D. D is the one with the lowest priority. And so we imagine that we are looking from the chiral carbon, the stereogenic center, down this bond to the group that has the lowest priority. Low man on the totem pole, the least important guy. We're looking there. And then we're going to see what are the other 3 doing. Here they are in order clockwise, rotating A to B to C. And that's called a right-handed enantiomer because these go clockwise. And the thing I learned in college was you can use your hands. So your thumb is going to go, you're going to have the chiral center at the base of your thumb and the tip of your thumb at that least important, that lowest priority. And then for right-handed, your fingers will curve around from A to C. So we assign priorities on those groups. We look at the molecule along the bond between the stereogenic carbon and the lowest priority group, and then we determine whether the remaining groups are clockwise to the right or counterclockwise to the left. Clockwise is designated R, and this is from the Latin word rectus, meaning right. Counterclockwise is designated S, from the Latin sinister, meaning left. So you probably didn't know that left was sinister in Latin, but it is. But right and R and rectus all start with R, right? So the R one is where the priority goes to the right. It goes in a clockwise order. So any questions that you can formulate yet? You know, this is bizarre stuff. Let's go on and talk about assigning group priorities. How do we decide who's more important? Well, you do these rules in order. The first rule is that we're looking at atoms that are bonded directly to that stereogenic carbon, and we're going to rank from highest to lowest atomic number. So the biggest atom is the most important. We're going to go from biggest to smallest. So in this example, if we have chlorine, oxygen, carbon, and hydrogen attached to a carbon, let's just draw that out. So here's our, I'll make the stereogenic carbon red because I kind of started doing that. I'll make the rest of these guys black. So if we've got chlorine and hydrogen, and there's an OH group. This one's kind of sticking out, and this guy. And then there's a carbon group, so that might be CH3. So here's our chiral carbon, our stereogenic center. It's got a chlorine bonded to it, a hydrogen, an oxygen. Yes, there's something bonded to this oxygen, but we're looking at the first atom we come to. And here there's a carbon. And so we look, which is the largest, which is the highest atomic number on the periodic table? Well, chlorine is number 17, so 17 protons. So chlorine has the highest priority. Next is oxygen with an atomic number of 8. Sorry, I'm not used to looking at that periodic table, it's weird. And carbon is 6, and hydrogen is 1. And so that's the order. Now, as I drew this one, you kind of have to use your imagination. So let's try to figure out what this one is, whether it's R or S. So we want to look this way, because that's the lowest, and this is priority 1, and this is 2, and this is 3. So you kind of have to imagine, okay, so I'm looking off from the side, and are they going 1, 2, 3 clockwise or counterclockwise? Can you visualize that? So this one is sticking out, and that one's sticking back, and this one's in the plane. So I'm looking in the plane of the screen, and this guy's sticking out like my stylus here, and that guy's sticking behind. So it would be chlorine, coming out is the oxygen, and behind is the carbon, right, in order. So that would be clockwise. So this would be an R, because it's going to the right. So this is R. If I use my hand and stick my hand from the carbon to the hydrogen and start my fingers at chlorine, I'm going to curve around to get the oxygen and then the carbon. I can't do that with my left hand. If I do that with my left hand to the chlorine and I go around the other way, I won't hit them in order 1, 2, 3. I'll hit them in the backwards order. Does that make sense? Kind of. Here, let me try drawing the other enantiomer. So there's the carbon. And we'll keep the hydrogen in the same place, and we'll keep the chlorine in the same place, and we'll just switch the other two. And I'll put the numbers back on there. So this is number 1, that's number 2, this is number 3, and that's number 4. And again, we're looking along this line from the carbon to the hydrogen. Now I'm going to use my left hand. I stick my fingers towards the chlorine, and as I curve my hand around, I'm going to catch the oxygen next, and then the carbon. You see that? It's left. If I'm looking this way, it's going counterclockwise. The hand thing always made more sense to me. And, you know, I'd be taking an organic chemistry class, and I'd be like doing this and just looking at me. My husband had never heard of the hand thing until I told him. He's like, wow, that's cool. It works for me. So your hand from the carbon to the lowest priority, you're giving him the thumb, I guess, and then point your fingers to the first priority, the largest atom, and see which hand works to get them in order. For this guy over here, my left hand works. So this is the left-handed, it's the S. This one, it's my right hand that works. I get my thumb to the hydrogen, my fingers to the chlorine, and then if I curve my fingers around, I get 2 and 3 in order. So that's the right-handed molecule. So the one over here is S. This is S. Any questions? Yes?
So you kind of follow your pinky?
I'm following the tips of my fingers. Like I'm going to curve around to grab onto something. I mean, it is my pinky, but it's all my fingers.
Yeah.
So I'm going to curve, when I curve my fingers, do I hit them in order? Okay, so we're out of time, we'll stop for there. But try to work on this and get straight in your mind what we're looking at. Go buy some gumdrops and toothpicks.